So alkynes, they can do a variety of different things based on what you have. Okay, so we'll go, let's have our generic alkyne here. Okay, our triple bond. All right, so there's two way. The first thing we learn about alkynes. Okay, if we have an excess, so XS stands for excess, and that kind of sounds like the same thing if you just say it, it's just the two letters. Excess, HX. So remember, the alkyne is a source of electrons, right? And then remember how we generate carbocations? We're going to generate our first product here, our geminal dihalide. So we get R. And then here, that's where the triple bond was. And we get our halogens. Are the halogens going to be on two different carbon atoms or on the same one? The same one, actually. So remember, this is a little side note, but remember, once we get to an alkene right here, once we get to the alkene, and here's maybe where X is, right? Markovnikov's rule. Now, if we add another hydrogen, this will disappear.
And it goes to the more substituted side.
It might be the more substituted side. And why might that be? What can the halogen do? Yeah, so resonance is key here. Remember, like I said at the beginning of the semester, resonance is going to be like everything that we relate things to. And that was pretty much true in this case. So there's a resin-stabilized carbocation here. Okay, so that resin-stabilized carbocation makes this group very stable. So it makes this position more stabilized. So you're going to go to the more substituted position in this case. Okay, so I just put that little side note. If you want to write that down, please feel free. But you want to make this as uncluttered as possible. Just take note of that. Okay, so what if we have a dihalide? How do we go backwards? So how do we generate alkyne? Instead of adding excess halo acid, we're going to add what? Oh, no. So going from the dihalogen, so the dihalo compound, how would we go back to the alkyne? We can't add acid because, we need a base. So remember when we learned about alkynes? You need a special base. It was that nitrogen base. So you can use two things. You can use LDA, or the one I taught you. Usually in this case, we use excess sodium amide, NaNH2. That would be our base of choice, okay? And two here. Then here's just the protonated. So you need a protonation source, H2O will do the job. So when you write, if you had to synthesize something like this, you would want to write excess, just to make sure everything goes to completion, okay? That one. So that's number one. So these are kind of like number one here. So this is reaction one here. This is called, let's use a little key. So right here, number one, this is called elimination. That's elimination, okay? And then here, going to the dihalo compound, this direction, this is called hydrohalogenation. Okay. But there's also another way. We also could do, there's another way to get to this alkyne. This one, okay? We could also use a vicinal haloalkane. So what if we had the two leaving groups? Maybe X is bromine. We have the two bromines or chlorines on neighboring carbon atoms. You can also also eliminate this with excess sodium amide and 2 H2O. So you can actually use both these. So this is also elimination here as well. So let's just say this is this one right here. This is reaction 2. Reaction 1 are these elimination processes. So we have elimination. So elimination, sorry I erased it. Elimination and elimination. So we can eliminate alkynes here to form alkynes right there. Okay? All right. Now, what if we only have one equivalent of HX? So HX. One equivalent. What's going to happen in this case? What stage do we stop at?
It only adds once, right?
Yep, it's only going to add once. Yeah, so we're going to stop at the haloalkene, and it's going to be on a more substituted position because of Markovnikov's rule. Like that one, HX, one equivalent. All right. So that will be hydrohalogenation, one equivalent. So this is our third kind of reaction here. Let's put number 3 on these conditions. We get to the alkene. But it's the same as number 2. That's still hydrohalogenation, but this is just one equivalent. Okay? All right, so we can substitute with alkenes. Now let's go through, let's see, what else should we do? All right, how about next? All right, for alkynes, we can actually add, we can get to a ketone. So actually, let me just put the conditions first. All right, remember we have hydration, and this is catalyzed by mercury salts. I didn't show the mechanism for the mercury, how it's involved, but that's not something you need to remember, okay? Just remember the product. So in this case, do you remember we did go to an enol, but what did that turn into right away? Yeah, we now know. We're now masters of polymerization, so that's a ketone. Okay, so that's a ketone here. So it goes to the more substituted side and forms a ketone. Now, if we did boration instead, so let's do 1, hydroboration oxidation, R2, BH. Okay? And then 2, H2O2, sodium hydroxide. All right, so we're still going to form an enol, but where does the alcohol end up? Bless you. So the less substituted, right? And when we tautomerize, what do we get? Is it going to be an enol, or what do we get? Yep, an aldehyde. Yeah, that's right. Yeah, because there's actually in this case, there's only one H right here. So the H adds to the more substituted side, so we're going to get the reversal selectivity. So we're going to get an aldehyde instead. Yeah, that's right. Good. Okay. So we can also add halogenation. So if we add X2, just one equivalent. One equivalent, what do we get with just one equivalent? So with one equivalent to alkynes, we stop at what stage? Yeah, so let's draw an alkene. Now, remember in this, the X will split up onto both atoms. So you're going to actually get X adding in a trans fashion, so anti-addition. So you get the halo, vicinal 1,2-dihaloalkene. Okay, so we can stop there. And sometimes, depending on what you want, you can actually make polymers or something like that using these type of reagents. So that's one benefit. But I think there's more economical ways to make polymers. But we could still get a variety of compounds. All right. Now if we have an excess. All right, so this is XS, not X2. Excess of halogen, so now we don't have just one equivalent. What's going to happen to the triple bond? Yeah, to an alkane, but how many halogens do we going to have? 4. So we're going to fully saturate this position with all halogens. Okay, so you're trying to form, I don't know why you would do this. I know. So sometimes some compounds with a lot of halogens on it, they become good flame retardants. So maybe they're using these compounds to test a new flame retardant. They're using materials. Okay, so, to stifle flames. So this is important in like fire blankets, lab coats. So you need a chemistry lab. You can't have a lab coat that catches easily on fire. You're working with dangerous pyrophoric stuff. It's going to be crucial that you maintain that. Okay. All right. And the last thing, the last two reactions. So you could kind of branch these reactions into several types, adding HX, adding hydrogen, adding X2, adding water, OH. So you're either hydrating or adding H and an X atom to form like a haloalkane, alkene, or you're fully saturated with like a poly substituted haloalkane. And then the other steps is reduction and then cleaving with ozone. So a lot of reactions, but the trends are very similar to the alkenes we saw before, and you can get a variety of different substrates. All right, so I'm running out of lines here, so we need just a few more here. Okay, so let's go. Let's start with 2 more. All right, so let's do this. All right, so this reaction is an important one we saw for synthesis. So if I take sodium amide first, number 2, I'm going to react it with a haloalkane, a good leaving group here. So that's that first one. And then we're going to have another one here. O3, 2, H2O. So ozone, so I think we saw this on the homework, but ozone, you can cleave an alkyne, but you won't stop at a carbonyl. So usually if you do a terminal alkyne, you will get a carboxylic acid, and you get off a molecule of CO2. Okay, so you get this carboxylic acid with the R group. You don't stop at the aldehyde, so it's not that useful for alkyne, but you do you're able to actually functionalize it that way. But you're going to cleave one carbon, unfortunately. So that's ozone. All right, so it's kind of hard to stop at this this one, okay? And that's the only one. I would say put an asterisk by this reaction here. Not really. I would say not really that important because we didn't go over it a whole lot. All right, but if we take a terminal alkyne here, treat it with base, what's the base going to do? It's going to deprotonate. Deprotonate what? Yeah, what's on the triple bond? The hydrogen, right? And then when we take that, we're going to react it with this alkyl halide, and we're going to generate a terminal alkyne. So now we form a carbon-carbon bond. So alkynes is like the next step where we can form new carbon-carbon bonds like that. Yes. All right, and then the last two here, we can take alkynes, and then there's 2 things we can do with it. A bunch of hydrogenation reactions. So let's take this down a few steps here. All right, so if I have hydrogen and Lindlar's What do I get? What's my product there? Do we remember? I might have put this like on some synthesis problems in the homework.
Doesn't make an alkene?
Yes, an alkene. Which one is it? Cis or trans? Cis. I don't know a good mnemonic for this one. Lindlar's likes the cis alkene. It forms the cis alkene. So it partially hydrogenates. And that's because the catalyst itself is already inhibited by a certain compound. So it only allows to add hydrogen once to the alkene. So the catalyst kind of controls how many times you add. All right? But if I don't have control and I just use hydrogen without any special catalyst, so say I use palladium or platinum, what's going to happen to the triple bond? Is it going to stop? No, so it's going to go all the way to what functional group? Yep, an alkane. So why would this be useful? Well, if you have a very long compound, like say you have a compound that was obtained from like dairy or something, and it's an alkyne, or you made an alkyne from that, and you want to make like butters or spreads, margarine, oils like that, you would partially hydrogenate it to alkenes, and that will give it a profile where it's now of a softer consistency because of the cis double bond. So that's how we take advantage and make food products there. All right, so it's hydrogenation has a role in industry. All right, so that's that one. But if remember this sodium one, this pesky sodium one, the mechanism of which I asked on the first exam. What happens if I have sodium in liquid ammonia?
This one makes a trans alkene.
Yeah, so if the other one made the cis, and there's only two types of alkenes we can form, right? So this one is always going to be the trans alkene. So then, guys, so I would say the most useful one of these here. Which reaction do you think is the most useful? Do you guys remember like what kind of reactions do you see for alkynes that was asked previously again? I think I could name 3 of them. And I'll highlight them for you. This one, extending the chain. What about another one?
Wait, what are we doing?
So let's highlight the ones that you think are important for like synthesis. So for synthesis, we care about reactions that produce only one product, and how can we use that in further reactions? So I think the ones with the halogens, like X2HX, not synthetically useful for us unless we're trying to go back to like an alkene or alkyne. But I think some other ones, if you need a ketone, this one is important for synthesis if you need a ketone here. Let's highlight these. Hydroboration, if you need to go to an aldehyde. Okay. Ozone, this one for ozone, I wouldn't recommend very much. But what if we need an alkyne and we need to go to a specific alkene? Those are useful for synthesis too, so these ones as well. Now, going all the way to the alkane, you won't be able to do anything because you can't further functionalize that anymore. So it's not going to be as useful. So those are the ones synthetically useful, I would say, in synthesis. Okay, but to form an alkyne, those reactions are useful too. So dihalo, well, I don't know how you're going to form a dihalo compound right there, but this compound, we can form this by reacting from an alkene. So we can actually get to an alkyne. So that one's actually useful as well. Okay? So getting to the alkyne, making terminal alkyne, going to alkenes, and then hydrating them to get the ketones or aldehydes. Because remember, well, we start with alkyne, and we go to a ketone, and I actually do a Wittig. That's how you would propose it. Okay? So those connections. Yes?
The trans alkene is an R group, right?
Which one? Oh, sorry. I guess I lost my train of thought. Yes. Where should it point? Up. There you go. Okay, so that's alkynes in a nutshell. The important parts, alkynes are acidic, so now you could deprotonate them with a suitable base, do SN2 type chemistry, this pathway going down to the R internal alkyne. Maybe I just put little numbers here. So this is our 4th reaction. 5, sorry. Eight here is, let's put a star by it. Not that important. Not that synthetically useful either. I think the only thing useful about this is if, say you have alkynes and, you know, it's like contaminating something. How do you get rid of it? Okay, well, maybe we could treat it with ozone, generate carboxylic acids. That's potentially useful, and CO2. You break that down. Okay, so that's number 8. 9 here was the alkylation. So that's our 9th reaction. 10 was the transalkene hydrogenation process. 11 was full reduction to alkanes. So you know in oil, you know, sometimes they have a mixture of compounds. Well, you don't really want alkenes in there or alkynes, so you would hydrogenate them all to alkanes, and that's how you get gasoline. Those burn better because they have more hydrogen/carbon bond content, single bonds. So that's why we would do those. All right, that is alkynes, and I know I made a little mess here, but that's alkynes there. Are there any questions about alkynes? There's one we're missing. If we're missing one, don't worry about it. This is all you ought to know. All right, so that's alkynes. Any questions about alkynes? Okay, so my recommendation, like this is cumulative, so like for synthesis, you might expect like new material, like carboxylic acid type chemistry for a synthesis target, but I might mix in there, like for a different one, you know, some other reactions, right? Like in synthesis, we saw a lot of Grignard additions, lithium additions still for alcohols, oxidations, PCC, or reductions, sodium borohydride, lithium aluminum hydride, those ones. So those are like kind of like, those are like the 4 tools that we have to form carbon-carbon, lengthen the chain, and, you know, reoxidize, reduce to get alcohols, or oxidize to allow us to extend the chain again. And then if you need to shorten the chain, you would have to use ozone. That's pretty much the only technique we know how to do. For sugars, you can actually do a lot more, but that's not important. Not for us, because one, it has to be a specific functional group, sugars, so it's not very applicable. Okay, so that's just things I want you to think about. Okay, all right, so now let's move forward to the next topic. So after alkynes, what did we talk about? Does anyone remember what we talked about? Benzenes, right? So we talked about aromaticity and all that. You don't have to worry about aromaticity, predicting aromaticity. I don't think I'll ask that again. But one thing we should remember is the reactions of the conjugated pi systems. And there's one reaction in particular we went over that has a special name. We probably remember it. We did a lab on it as well. You guys remember what reaction that was? Yep, Diels-Alder. And why is this so important? Well, it's a very powerful tool for making carbon-carbon bonds and rings. And that becomes important in like making steroids, like the hormone compounds. So like hormone therapy and all that, that's become an important part as a supplement, but also an important reaction. All right. So you notice I mentioned outside the Diels-Alder, there's like reactions like that. I kind of brushed over that and mentioned it, but you don't have to worry about that. We're not going to worry about that. The most important one is Diels-Alder, and that's the one I'll cover here. All right. So this is, all right, I'm trying to remember, what chapter was that? Was that 19? No, that sounds like aldehydes and ketones. All right. Well, yeah, I made it 17 or 18. Okay, this is conjugated. What does conjugated mean? Oh, so it's not, so rings are the most common. So they give you very wide colors, but it's actually anything with alternating what type of bonds? Double bonds, right? Alternating double bonds, right? Good. Conway pi systems / DA reaction. Okay. All right. So number 1. Preparation of diene. So I kind of tested also on the first exam. Preparation of our dienes here. How did we prepare our dienes? So I gave this example. I don't know if anyone caught on to that. On the actual exam, but I gave this example. How would you go from here, or what would this do? You have this and something like terbutoxide. What would this do? Would this do SN2? No, it's too bulky of a base. So terbutoxide only does SN2 on methyl substrates. So that's pretty limited. That's like only one compound, right? So it does not very much variety. So not a lot of stuff you can do. So what is this going to do primarily then? All right, attack the what? Oh, okay. No, it won't attack the double bond either. So what? So no, that's a good guess. So what kind of reagent is this? Is this considered a base nucleophile? What would you classify terbutoxide as? Bulky base. So let's put in parentheses bulky base. Yeah, I know there's a lot of reagents we used, right? And you might be wondering, oh, okay, we'll just have to remember that. So we have to be able to classify it and recall our E2 knowledge. Okay, so if it's a bulky base, it's primarily going to do what kind of reaction? Is it substitution? No, not SN1. E1, yes. So mainly E1. So SN1 usually is for nucleophiles that are neutral, like not strong bases at all, like very weak bases. So that would kind of that would kind of like make you disregard that. So if it's a very bulky base, strong base, you're going to disregard any like SN1 or E1. So it's going to be elimination, which is E2. So we're going to form a double bond. And we're going to form our diene here. So we have strong bulky base. So that's how we make our dienes. We make it from elimination. So this is going to be an E2 mechanism, E2. Okay. And then, so preparing dienes, so we get them from, so this is what we call an allylic. The allylic position, 1 carbon over from the double bond, allylic halides. Okay, and you also form it from dihalides as well. So dihalides as well here. All right. Let's use a different base instead. Sodium amide. Excess. All right, sodium amide, what would you classify that as? Strong base? Yes. Strong nucleophile? Not really. So sodium amide, in rare cases, it will do SN2. Methyl is like the only example. But all the examples I kind of gave you in the past, it's going to be elimination. So what am I going to form instead? So not SN2, but yeah, we're going to form double bonds. Where am I going to form double bonds? Is it in the middle? Yeah, so you might think, okay, couldn't we just have in the middle and then but then you still have a bromine there. And then you can't eliminate that anymore because you don't want to form 2 double bonds right next to each other. That's not common. So forming down the middle, you get a situation where now you have an alkene, now you have a proton source. So you could probably just go back and forth between the alkene and just going back to the alkane. So we're actually going to choose the sides here to form the diene because the diene actually has resonance structures and that makes it a little more stable. So that's the more stable product. So we're going to make a diene here again. All right, so that's going to be our diene, okay? So we got preparation of dienes, allylic halogens, and then dihalides. So we kind of, that's our two examples here that we have. All right, now this is where we introduced the second class of reaction. We introduced the concept of, do you remember? Kinetic control, thermodynamic control. That's also called 1,2 or 1,2, 1,2 or 1,4 addition. So electrophilic addition. So it also behaves like an alkene. All right. HBr. All right, so let me just refresh our memories here. So the simplest system, 1,3-butadiene. So that's our simplest conjugated system. Okay. All right. Now let's say we add only one equivalent of HBr. Okay. So where would I protonate? Am I going to protonate at the internal carbon? Or it's on the terminal carbon? External. Because you want to generate a carbocation that is resonance stabilized. Okay, so you want to generate this carbocation. So it's going to go through this carbocation. That one is resin stabilized. If you protonate at the internal carbon, your carbocation will be primary and no resonance. This is secondary and has resonance. So this is the preferred mode of action. Okay. All right. So in this case, you're going to get two types of addition here. So this would be called the 1,2 product, Br. And then if I do a resin structure here, where will the charge be for this other structure? At the end, yep. Now, you might be wondering, this is a primary carbocation. Shouldn't that be really unstable? But what's special about this carbocation? It has some additional stabilization, right? That's due to what? Conjugation and, well, yeah, conjugation, but what's the other thing we can draw here? Starts with an R. Yeah, we draw resin structures. So yeah, it has that's actually a good point. Extra conjugation from the pi bond, right? That too, that's good, yeah. I wasn't expecting that. That one, and also resonance. So that's the other stabilizing factors. Very good. So we get two products here. We could attack at the end as well. Okay. But depending on your product or your temperature, you're going to get a ratio or mixtures. Okay? And by analyzing these mixtures, we kind of understand like how this reaction works. Okay. So I'm going to give you two scenarios. At cold, what's cold? All right. So think about it this way. If you have enough energy to react, that's going to be under thermodynamic control. So you're going to form the most stable double bond. But then kinetic is like, when you think kinetic, right? What do you think? What do you think about? Like when you think of kinetic energy, maybe from physics, what do you think about? Energy. Yeah, energy. But energy to do what? Like in reference to what? So there's two types of energy, right? Potential energy. Well, that's due to the position. But what's kinetic energy? Movement. So you're going to think, okay, which one forms the fastest? Which one collides, has enough energy to get the products, right? So that's going to be the one that has, think about these two resin structures. Which one will you think react the fastest? Which one is more stable or more likely to form? The 1,2, because I'm going through which carbocation? A more stable secondary, yes. So at 0, you would get this at 71%. This is just numbers, so just write these numbers down. These are actually from experiment. 15%. Now, if you went even lower, you'll probably push it even further. So that's why temperature is a good measure of control. So we could actually change the temperature is like one of our most important variables for controlling the outcome of a reaction. Okay. Now, if I raise the temperature to 40, okay, what do you think is going to happen when I have the 1,4 adduct? Oh, wait, did I write this right? Yes, I did. Okay. The highest amount at the higher temperature, right? 85. So it switches. So these yields are high enough that if you did this on a gram scale, it'll be viable. So you say you have a gram scale, right? Or you have 10 grams out of here. Out of the 10 grams, you would get 7 grams of the 1,2 product. You could isolate that. That's pretty good. Like industrially speaking, that's pretty good. All right. Now 50%, that's like saying, oh, I get 1.5 grams for every 10 grams I put in of starting material. That's not a good outcome. That's very low. So on a industrial standpoint, that would be something they cannot afford to do because they're operating at a loss of most of the product they put in, not very good output. Okay, so that's what these numbers could kind of mean. Besides like adding to 100%. All right, so the selectivity changes because look at these two products. Which one you think would be more stable? Remember double bonds? What was more stable about double bonds? Internal, because why is internal more stable? More carbon atoms surrounding it, right? Remember, more carbon atoms will stabilize the alkene by hyperconjugation. Yeah, good. All right, okay. So we can also do this with, should I use a new page? All right, let's go over here. Can you guys see that? All right. All right, you can also do this with BR2. The only difference is, what's the only difference you're gonna get with BR2? Yeah, instead of 1 bromine, you're going to see how many in the product? 2. Yep, that's it. All right, so the adducts are the same. You're going to get 1,2 bromo. So the bromos are just next door from each other. So 1,2 bromo. So that's the 1,2 product. 1,2, and then, or you could put adduct here if you want. And then what's the other product going to be? Yeah, 1,4. So yeah. So you get the 1,4 product instead. Yeah, so on the rationale here, can I zoom out? No. Yeah, I don't know why. I think it zooms too much. All right, that's 1,4. Okay. Are there any questions? So that's conjugate pi systems. The only last thing we have to talk about is Diels-Alder. And I'll do that, then we'll take a little break here, okay? All right, any questions about electrophilic addition? That's where we get the term kinetic control, thermodynamic control. So this one would be the kinetic product. This one will be our thermodynamic product because it's more stable at higher temperatures. All right. So 1,2 is usually always kinetic, thermodynamic. All right. So I'm going to put a new page here. I'm not going to fit Diels-Alder on here. So let's do that. That's right. I'm going to put a new page. All right. Diels-Alder. So this is still part of conjugate pi system. So Diels-Alder reaction. Yeah, sorry, number 3. All right, so generally speaking, Diels-Alder, you have a cis, S-cis diene, and On your dienophile, you're going to have something that's electronegative. So X is a electron withdrawing group. All right, let's put that on the side here. X equals EWG. So fluorine, trifluoro methyl group, nitro, aldehyde, ketone, ester, you name it, that will be your electron withdrawing group. All right. So I didn't really teach you retro Diels-Alder. Don't worry about retro Diels-Alder. We're just going to focus on Diels-Alder. So if I add heat here, what's going to happen here? Yeah, it's going to do that ring forming, right? Bam, bam, bam. So like, I don't know. Personally, probably the most beautiful reaction in chemistry. Everything happens at once, and it just snaps shut, and you form rings so easily. You just have to heat it. Say less. Now we form that ring. Okay, so you just heat it, and we saw that in action, right? We left one running for a week, and it just formed over time. So that's pretty cool. Although, so that's how we take advantage of that reaction. Okay, so if you follow the arrows, you're going to form a cyclohexane, right? And then your alkene, you're going to form an alkene here. And if you don't need that alkene, you can hydrogenate it with hydrogen. Very economical to do that. And depending on what's on your dienophile, you can get a variety of different substituents. So it's very easy to form these rings. Okay. All right. So one thing we have to think about the stereochemistry. So the only other thing we have to mention is that the stereochem is, it doesn't get flipped or anything, right? It stays the same. It's retained. All right. So you see an alkene and a diene, and all you have is heat, you should automatically think, okay, Diels-Alder. That's all you should think about. You should not think about, SN2, E1, E2. None of that really happens. Okay, you're going to get a cyclohexene, and your groups are going to stay the same. Okay, so this one actually has no enantiomer because it's symmetrical. So no matter what, you have a meso. This is a meso compound, so you won't have any enantiomers. So here you have the X's are on the same side of the alkene, and the product, they will be on the same side of the molecule. Yeah, Catherine.
And then actually you gave us like a little guide of like what's in and out on the day.
Don't worry about that. Yeah.
So we won't need to like how that even though they're.
Yeah, you won't. You won't have to worry about that. Yeah, I wouldn't worry too much. About that one. If you did, that I would say maybe put that like little guide maybe on your note card. That'll be I think good to do. But here, generally speaking, just refer back to the stereochemistry on the dienophile. I think that's more represented here. Okay. All right. What if we have a trans? What if we have a trans dienophile? What's going to happen to the X groups and the product? Yeah, stay trans. So we're going to represent that using wedge and dashed bonds. And it doesn't matter, it does matter how you draw it because you're going to get two pairs of enantiomers. So a pair of enantiomers here. So X, whatever X is. And then you're also going to, so this is not symmetrical, you're also going to get what in addition? Plus, what's the other stereoisomer? Yeah, the enantiomer, En. So the enantiomer in this case, you'll swap the bonds, the double and the double bond. Sorry, not the double bond, the wedge and dash bonds of each other. So you might think they're mirror images, but they're not. If we try to mirror them, they're not mirror images. All right. So that's for like simple rings, like we don't have one rings. Okay. You can also do this with alkynes. So I think I showed some examples of alkynes, but maybe not a whole lot. So this is also an example of a dienophile, because you only have one multiple bond here. OR. And this gives specific products too. So instead of forming just one alkene, how many double bonds are you going to form here? Two, right. One of the triple bonds gets used, or one of the bonds in the triple bond gets used to form a carbon-carbon bond. So you're actually going to form isolated double bonds here. And that's there will be actually no stereochemistry for these esters, and that's because there's no saturated carbon like that. And you get only one product because this is also, again, symmetrical. And yeah, so the only stereocenters you could potentially have are on these carbons, but I would say don't worry too much about that. If anything, for Diels-Alder, might ask you, like, okay, how do I form this, like, in the synthesis? I'd be like, okay, you form these two reagents. You get the two reagents. Oh, how are you going to form a ring? You're going to use Diels-Alder to heat and add them together. That's how you see the synthesis. All right. So I'm going to move these pages, move this up a bit. All right. So the classic example. You don't start with a linear diene. You start with a ring with a diene. So cyclopentadiene, cyclohexadiene are the two most common examples. And we did one example in the lab this semester. All right. All right, what happens here? So what's the primary product you form in this one? You're going to form a fused ring, but it's going to be, you're going to have a bridgehead. Where's the bridgehead? Yeah, the point right here. So you're going to have a point right there. That's your bridgehead, okay? So that's your nose of the ring here. So remember, in the bridgehead, my recommendation is you kind of draw this like, I don't know, one of my other students, I guess, put it in a good way, a paper airplane. I don't know. But I don't know how you would draw a paper airplane. And then here's your double bond, right? Now, what products are preferred? We saw this in the lab. Is exo preferred or endo? So exo would actually be the most. So exo would actually be thermodynamically. That's thermodynamic. Let me rephrase that. What forms the fastest? Endo. And that's because these groups right here, CHO, are pointing away from the bridgehead. So you have less steric hindrance. So this would be, oh, sorry, can you guys see that? Oh, man. I had to go back to using whiteboard. All right, so this is endo. Let me just move this up a bit. Sorry about that. I blame the technology of iPad. Everything works with like PC. Everything's like right aspect ratio, but for iPad, it's just like, ugh. Okay. So endo is preferred. So this is the kinetic product. All right. So typical question I might ask. All right. Ring, dienophile, predict the endo result. So that'll be you would want to draw the endo. Okay. Now, how do we predict what's endo on these other examples here? Well, remember endo The endo product is usually the one where the X groups are pointed downwards and away. So they're usually, if I recall from what we talked about, they're usually the enantiomer, or the series of enantiomers where the X groups are kind of pointed away from, pointing down and pointing underneath the alkene. But for endo, what you really have to worry about is when we have bridgeheads. That's usually where it's more important. Which one is endo when you have a bridgehead? So when you have a ring. Okay, that's usually where we ask, like, oh, which one's the endoadduct, which one's the exoadduct? Because for these other examples, when we have just one ring, it's harder to see which one is endo unless you have that guide, which I showed you in class. Okay, all right. So let's take a break before we start reviewing benzene reactions. Okay, so that's Diels-Alder. Let's take a little break here first, and then we'll resume at 4:10 or 4:12. A few extra minutes. Yes. Yeah, sorry. Let me bring that up here. So this is the kinetic adduct. Yeah. So that's the kinetic adduct. All right. Also, guys, if you want to get the extra for notes, I will check that today at the end of class, if you have them. Because we're pretty much done with new material, so.
Wait, what do you mean?
25. Extra credit, for the homework. Remember, if you take good notes, I'll add 25 points to your homework category.
Professor, I'm a little confused. How do we make this structure?
You made it.
Like I did, but I don't know how to make it from these two.
So that's the CH2 right there, right?
Okay.
Remember the double bond migrates, so the double bond is right here. Now, so this is, so if you count here, 1, 2, 3, 4, 5. So that cross, that's not actually a carbon atom. It's just a bond behind another bond.
Oh.
So that point, see that cross right there?
Yeah.
See where that cross is right there? That's not a carbon atom. That's
Okay.
just two bonds
So
overlapping
it's only
close to each other.
1, 2, 3, 4, 5,
That's
6,
not
7,
that's not a carbon atom.
8, 9. Oh, I got it because
so 5, 6, 7, 8, 9. Yep,
yeah,
you got
oh,
it. That's
got
it.
Okay. Got it. Thank you, Professor. I think that's where you stop.
Yep, that's right. Good. Yeah, I'll have a pen.
I don't know.
I'll have a pen. Don't worry.
And then click on their whole. And then,
All right, thank you. If your score's not, so that assignment, if you don't see a score for it, just reach out to me and I'll, in case I forget, okay? But you should be good. There you go. You're welcome.
and then you just fill out whatever you
You'll
apply.
try to know
Like, switch to
after
this.
class.
Yeah, today or on Thursday. So you still need to rewrite some notes. Come back on Thursday.
Info sessions. Go to the info session and go to at least one office hour. So they see your name. And then you just have a good interview. And you get in, you get in. And then I would say what you should do is during the fall, look up the names in Instagram, all the clinics, and then see when they post their cycle program. And I would say just apply that. Or just try to do a couple. I say no.
Another one that's open right now?
Let's see which ones to apply to.
Are you checking notes at the end of today's lecture? Or do you want to check them now? Because it's just review.
Yeah, just speed review, right?
These people have a rate. Or like,
And John.
do you also speak Hindi? This clinic right here gives like really high priority if you speak one of these languages. It's like and Hindi. So it doesn't guarantee you a spot, but it gives you.
It makes it like look better.
Yeah. Paul Hahn is a really good clinic, but they're crazy strict.
Why is that?
Just the people running it. And then this one's a good one, but if you don't speak Spanish, you're probably not gonna fit. Armani, I would say This one is really good too. I am Young, the
Mhm.
Filipino community. This is the one I was in.
Oh, yeah.
Willow Clinic, I'd say Willow Clinic,
Whoa.
Paul Hall, are the big three.
What if I look up their Instagram?
Yeah. So if you don't get any of them, and then let's just say spring coming, spring around, join this one. This one is the best one, but it's also the hardest one to get into. You will get more experience, because we get a lot of, like, homeless people.
Mhm.
Series, it's like version care.
It's like every Saturday?
Every Saturday, all of them are every Saturday,
Okay.
but you'll have to do, there's other things like meetings, like social outreach, and things like that, so you get everything, the community service, the clinical hours, like shadowing,
Mhm.
and a letter right from the doctor,
Okay.
for everything. Yeah, there's a lot of, but I'd say Willow, Money, and Paul, but this is.
Strict.
Really, they're all strict, but this one is like, just really, really trial, you know, but, yeah. Willow is the hardest one, they accept the least amount of people, and they have the least amount of cycle.
Oh, okay.
Yeah. But that, if you can get this one, that'd be pretty fun.
You know when it opens? Fall?
Willow only opens in spring.
Oh.
So for example, let's just say fall and winter you try,
Mhm.
and you didn't get into the other one, apply to this one.
Okay.
Yeah. But you have to do it in your third year. They don't usually take fourth year. Very rarely. So, it's a try to get in one of these this year. And if it's either for Willow or for Ramon, you always text me, and I, if it's mine, I can give you some of the interview questions, and it's this one, I can give you some of the interview questions. Yeah. Really good experience. This would like cover most of what you need
For med school?
for med school and pre-health. So like, you got community service, clinical hours, shadowing. you know,
Almost
those,
everything that you need.
Yeah, and if, within the clinic, if you get chosen, you can do research with them as well, which is what I do. So. it is-
Yeah, the application was open, but it closed on April 19th. I didn't know.
Wait, something?
For Willow Clinic, their application opened.
Yeah, but they probably would not let you apply because you're not,
I'm not there yet.
you're not like, yeah.
Okay.
But, yeah, they're all pretty good.
I just have to keep an eye out for whenever these open.
Just be proactive, check it out,
Mhm.
apply it to you, and then go to their info session. And just, you know, gotta do it quick, just, be like, hey, you know. I haven't been able to, but I'll be honest though, it's all student loans, so.
Yeah.
A lot of it, it's like, basically every Saturday, that's where you meet with the doctor from UC Davis
Mhm.
and all the med students. But like, because it is student run, like when you interview, a lot of it's like a vibe check, so. Yeah, you could technically say all the great things, and then
Mhm.
they could just say no, because they weren't feeling it. Sucks, but.
Why would they reject you though?
Well, either you had a bad interview or they just didn't like you. Like last year, or not last year, but like in my final year, I was in the interview team.
Mhm.
There was just some like mean girls in there, like
Mhm.
on the panel with me. And then there were some really good people. Those girls were, I don't like her. And then,
Yeah?
yeah, it's a low, so. So when you get in, or if you don't get discouraged, sometimes it's just people are weird. Yeah.
Your number's still the same, right? 530, oh wait, 510 282?
Yeah.
Okay. If I not in a group chat with someone from last semester.
Let me know. And if it's Amani, I'll fuck with it. She can be yeah. She was an organizer.
Rachel?
Yeah, so they conduct.
She'll help me a lot.
Yeah, they conduct interviews differently.
All right. Is there another notebook or is this it?
Amani is
There's
You were on the back. Here.
It's because I ran out of space yesterday, but I started it on this one.
Yeah. All right. You don't need that's just review over there, right?
Yeah.
Good.
It's really good, at least in that. It's really good to learn. Sometimes it's good. So, let's say there's a lot.
I've been checking it pretty regularly, so
It's not that they don't.
should be good.
If there was only a couple steps to go, and there's a third year that's gonna be essentially 1, 2 years, 2 plus at least 2 years, they're gonna take them over some of it's just like one. That's why when they apply them, you would essentially, they want people in building their experience. I would be
All right. Thank you.
That's nice.
Here you go. Yeah. What's up?
I
Wanna check
added, I finally, I had to like, I had them all in this notebook.
Have you ever showed me them?
I showed you the general ones,
Oh,
but again,
sorry,
the
this is your lab
conclusions
manual,
were
okay.
all, hold on, where is the starting page? 'Cause
Oh, good. Okay.
again, I had it because like I would start some of the pre-labs before.
All right, got it.
The post
And
labs?
then no problem submitting the form this time, right?
No problems,
Okay,
yeah,
good.
like, against.
Oh,
the-
that
actually,
that was last one.
Yeah.
Okay, no worries.
The Deals Alder one, I don't have it in the notebook because, again,
Where's
he
it?
gave us a separate sheet.
Oh, but do you have the discussion in here and conclusion?
I have it on sheet too.
You have to sign it.
All right.
Yeah, once.
Everything was done, because again, you gave us the separate sheet, so you said just to submit.
Okay. And then the discussion and conclusion. You
The
wrote on this-
conclusion?
the last page. Okay, got it. Just want to make sure you include that. Oh, okay. Sorry. I realize you. Okay, good. And then the Zalder, yeah, this one. Okay.
Conclusions on the other page, because,
Okay.
go back,
More.
because it's two separate times.
Oh, got it. Okay.
Because we started it, and we used the stuff, and then you gave us this
Yeah.
handout.
Okay. No, that's good. All right. Nice. Thanks, Catherine. Okay. No, you did a lot of work there, so good work. All right.
More organized, but I was just like, there were so many different post-op questions we were printing in. They found it.
Yeah,
I wonder
yeah,
if next semester you would
definitely.
like allow a binder instead.
Yeah, that would help you, yes. Like
Yeah, the binder would be
binder,
helpful.
you know, like what Michelle did, like those.
Yeah.
But it might be too much stuff for like those folders, but like a lab binder or
The
like.
lab binder would be nice. Just
Yeah,
because
or,
having
you
to
know-
cut stuff out and then like.
Yeah, you could just put it in there. I could check it like a little portfolio thing. Yeah, it would work. Yeah, okay. Good. Thank you, Catherine. You good? And I know you took your notes, but you don't want extra credit for taking your notes. You know, like that 25 points. I think.
Is it? Do I just show you my notes?
Yeah, and I would make sure everything's there. You get 25 points. Add to your homework score. Just a little buffer, but if you want it, yeah.
So
Okay.
you said for active homework, if we write it down, there's like extra credit that we get?
No, it's your lecture notes.
For lecture notes?
Yes.
Oh, not
all
active,
your-
okay.
I'll add the points to your.
Oh, okay,
Yeah.
okay, got it.
Okay, are we all back? Well, most of us are back. What's up?
I have a question. You probably checked that, but I just want to make sure when you gave me the extension for the active, I did do it. Are you going to grade that?
I'm going to
first?
upgrade it. I'm going to update it at
Okay.
the end. Yeah.
Okay.
All right. All right. We're I just forgot one reaction here. Okay. So let's go. Now the last one of this one is allylic and benzoic bromination. Okay, this is one with MBS. So if you have an allylic position, for example, this alkene here, well, let's not put it there. Let's put it right here. Okay. You can use something called MBS and heat. So MBS is N-bromosuccinimide. So now we can actually comment on like what MBS is because we talked about anhydrides now. So we can actually talk about that structure, right? So MBS is this anhydride structure. That's called an imide. So that special imide, when you make it, it's a specialized reagent. But basically what happens, it has bromine. It has a small amount of bromine in it. And it's allowed to do bromination. So what you get is allylic bromination. And since this is symmetrical, we don't have to worry about any side products here. So we get N-bromo at this position. So like for synthesis, I usually choose reagents that give you one product, so you don't get a mixture of products. Because if you get a mixture, you might, depending on what you're trying to do, it might not work out 100%. Okay, so that's N-bromo. So you can do this. This is for the allylic position. But then if you have a benzene and it's at the benzoic position, we learned about the benzoic when doing carboxylic acids, right? So as long as you have a position with a benzoic hydrogen, so this will be my benzoic hydrogen, benzoic H, okay? And if I treat that with MBS and heat, at the benzoic position, what am I going to put there? Bromine, yeah. So that's the bromine position. Good. So we'll get so that's the last step. So the reason why this works is because we have a conjugated pi system, and the radical that would form at the allylic position can be resonance stabilized. So that's why it's the most favorable. So we get N-bromo succinimide. You can also use NCS. NCS will also work with Cl if you need Cl. So there's two variations. And the iodide one is not commonly used, so I wouldn't worry about iodide. Okay? If you want to put iodide on there, you could just do SN1 reaction or SN2. So there's no biggie. Yeah. Okay, so that's the allylic and benzoic bromination. So useful transformations at the position, one carbon away from the benzene, one carbon away from a double bond. Okay, any questions on? So that's the conjugated pi systems. So now we're going to go on to benzene reactions. Okay. All right, so I'm going to make this clear and concise for you, so it kind of, it kind of brings all your notes into focus towards the end here. All right, but are there any questions on allylic and benzoic? Okay. Mechanistically, this mechanism, don't worry too much about it. We went over it, but it's radical. So I'll say this is a radical reaction. So whenever you see like a bromine compound and heat, usually a radical reaction. Just, it has to have Br2. Like it can't be HBr. HBr is usually polar addition. But if it has radicals or Br2, heat, usually a radical process. All right. All right, that was 4. Allylic and benzoylic bromination. All right. Okay, what chapter was benzene? Was it 15? Okay. Benzene reactions. All right, we spent a lot of time on this subject because benzene, I don't know about you, but benzene is everywhere. Benzene is probably in your favorite products as a preservative. Benzoate, sodium benzoate. It's in like your common daily over-the-counter drugs that you can just purchase to treat a headache. Aspirin. We saw in aspirin, salicylic acid. And it's all these other kind of medications like morphine at the hospital for pain management, stuff like that. And all these other types. So it's a very important core in a lot of pharmaceuticals and a lot of medicines that we see. All right, so let's start with our benzene reactions. Okay, so there's a couple we'll go over, and hopefully they ring a bell here. All right, number 1, BR2. Aluminum tribromide. What does that do? Yeah, we're going to add a single bromine there. So you're going to get halogenation, so bromide. That one. All right, we can also add chlorine. What are my reagents for chlorine? So not sodium. Yeah, use aluminum. So aluminum is a great Lewis acid. Sodium is not, and that's just because it doesn't have the high enough valence. So aluminum trichloride, and what halogen do we use instead? Not Br, but chlorine. Yep. So chlorine gas. So chlorine gas is like easy to work with. It's all right. All right, so that would give us our chlorobenzene. Good. Okay. Yeah, what's up?
For the bronation, why is it just BR, not BR2?
Oh, my bad. I didn't catch that. Thank you. All right, BR doesn't exist. That's the atom. It doesn't exist as just BR. My bad. Maybe in space, but not here, not on Earth. All right, how do we add a nitro group? Yeah, so you need a strong acid. So HNO3, H2SO4. There you go. You got it. Great. So almost halfway there. Okay. Yeah, my bad. It's all right. No, poor writing here. HNO3. Yep. All right. Okay. So with to get the sulfonic acid, we will need something called fuming H2SO4. But let's replace fuming. What does that mean? That means you add sulfuric acid with a little bit of sulfur trioxide, so SO3. H2SO4, that's commonly what you saw on an active. That will give you the sulfonyl group, or SO3H. All right? And that's important because these aren't sulfa drugs, so that's how you would make it. All right. Yeah, Alondra. Oh, sorry. So fuming sulfuric acid, what that means, you have concentrated sulfuric acid. And it's SO3. It doesn't mean just erase that. Sorry. So when we say fuming, you would write SO3, comma, H2SO4. That's what fuming sulfuric acid is. It's called fuming because it gives off a gas. It looks like it's on fire. Well, not on fire, but it's giving off a lot of gas. It's fuming, a lot of exhaust. It looks like it's giving off a lot of exhaust. Yeah, you're welcome. All right. So we can put on a sulfonyl group. We can also remove it. How would we remove it to get back to benzene? You guys remember how do we remove a sulfonyl group? No, it's not DMSO. Yeah, we're going to do dilute water. So dilute meaning H2SO4, and it has water in it, H2SO4. So dilute acid with heat, and you also have to heat it a bit. Heating will get it started. Heat, you'll get back to the benzene. So that's how we can take off sulfonyl group, block it, block a position, and then put it back on. So that's a synthetic strategy. Very good. All right, so now we got two more, the Friedel-Crafts reactions. So let's draw an arrow here. Sorry, a little weird. All right. So Friedel-Crafts, what if I add acetyl chloride? So acetyl chloride and Lewis acid, AlCl3. All right. So I'm going to add what group to my benzene? Yeah, we're going to add the acetyl group. COCH3. That's the acetyl group. The chlorine goes away, so you don't actually add that. So that's the acetyl group. Good. All right, and then the less useful reaction here. Not Friedel-Crafts acylation. So this is called Friedel-Crafts acylation, number 6. This is F.C. acylation, but there's another kind of Friedel-Crafts, right? Not acylation. What's the other one? Alkylation. But unless you're doing a cyclic type of reaction, not very useful because you get multiple additions. So in this case, we will use something like CH3, Cl, so any kind of alkyl group, and then the Lewis acid is the same, aluminum trichloride, or aluminum chloride, whatever pick you want. I'm starting getting a little cramped. Okay. All right. And then this one suffers from poly addition right here, CH3. All right, that's reaction 5. All right, in this mix, we also talked about phenol. So I'll probably leave a little extra space when we talk about phenol, okay? All right, so now some other additional transformations that we saw before. Wow, I never thought they... Oh, interesting. Huh. This reaction I never saw before. Okay. So... All right. So, well, we didn't counter this in the, we did not encounter this in this chapter, but now I can oxidize the methyl group with KMnO4, heat, and water. What does that do? Yeah, converts to carboxylic acid, right. So as long as you see KMnO4, acid, heat, water, any of those combinations, you might see in different forms, you're going to get carboxylic acid. So that's something we learned now in the carboxylic acid chapter. So we could form a carboxylic acid now, or we couldn't have done that previously, okay? All right, now what if we have, here, zinc amalgam or iron, HCl, tin, HCl. What happens here when we put these reagents and heat it up in the presence of a carbonyl group? So no, this actually won't make a carboxylic acid, and the reason is there's no oxygen in one of our reactants. One of our reagents. So it does something to the carbonyl, but think of it like the zinc is a good reducing agent. So it's going to completely reduce the carbonyl. So what do we get? Yeah, so we're going to completely remove the O, and we're going to get, just an ethyl group. We removed the oxygen. So we kind of deoxygenated it in a way. All right, so the other transformations we saw here, let's put it like that. So do you guys remember how do we go back to a carbonyl? So I don't think it was palladium, was it? There's a few ways. So to reoxidize this, you need a very strong oxidizing agent. So I think the one I showed you was trifluoroperoacetic acid, so CO3H. So that would actually put back on the carbonyl. So you can actually install the carbonyl back on if you wanted to, going backwards to the ketone. And I believe that's the reagent I showed you. Okay? Now let's talk about one more here. Yeah, I believe that's it. All right, but now we have to talk about nitro. All right, so how do I go from nitro to the amine? So there's usually two steps. Two steps is just acid-base workup. Sodium hydroxide. It's just to deprotonate the amine. Oh, my bad. This is now coming off the page. There we go. All right. How did we reduce the nitro to amine? So there's an here's another one. Or MCPBA. That's another one. All right. Do you remember how we reduce the nitro? It's very similar to the Clemenson reduction, which is this one. This one is Clemenson. Oh, damn. This is not good. I can see here. All right. So this one, this last one, see number 6 here? That's Clemenson reduction as we go forward. So the zinc will reduce that. All right. So here, to go back to amine, you could use iron or zinc, Hg, zinc amalgam, HCl, and heat. So if you do that, you would completely reduce the nitro group, and then it'll be protonated because it's in acidic conditions. Then you deprotonate it to get the neutral amine back.
Professor Andrew?
Yeah.
For number 6, to go from the CH2CH3 back to the ketone, we have it just as Jones in our notes.
Okay, Jones. Did I use Jones? Okay. Oh. Yeah, I think you're right. Thank you.
And that's
This is going backwards there, yeah. I thought that. Sorry. Thank you for clarifying that. All right, so here's like Jones reagent. So CrO3. Yeah, you're right. Jones reagent. Thank you. All right, and then going back to the nitro, you can do that, but you don't need to, I guess. Sometimes it's not necessary. And I think, is it this one that goes to the nitro?
yeah, to go that way.
Oh, thank you. Yeah, that's nitro. Here you go.
And it'd be, for the zinc amalgam, it could be also iron amalgam for,
Oh, yes. Oh, you mean for number 6?
yeah.
Yeah, so you could also use, in addition here, it could be also or Fe or tin. So those are the most common ones. You can also use zinc too. Zinc would work, but zinc amalgam's like the most common one they usually do, so we'll just leave it as zinc. Fe or zinc amalgam, HCl, for the nitro group. I think tin would work too, so I seen tin also worked for this one as well. So you can also use tin here too. Okay, so just a few more we covered in this class. So how do I go from... How do I make a protecting group here? So maybe let's my bad, guys. How do I go from... Let's see, we had to make this arrow exceptionally long. Okay. So how do I go from the amide? How do I get to the amide here? NH. How did I make that one? So this is actually something we learned now. Think about this bond here. That looks like I have an amine attacking to form an acetyl group. So what kind of derivative will we use to make that? Acyl group, yeah. Acyl halide, yeah, you got it. Cl, like that. Usually there's pyridine in here, so yeah, it would be pyridine. I don't know how to separate this. We're getting like kind of cramped. How am I going to finesse this a little bit? Sorry, guys. Let me put this 3 maybe somewhere else. 3 right here, forming the nitro. And let's put this arrow right there. Okay, there we go. So pyridine is usually a base just to mop up the excess acid that's produced. Now, how would I go forward? Now, this forward direction, I'm going to replace the amide bond. Instead of the amide bond, I'm going to free up the amine. So I'm going to, the most common thing to do is to hydrolyze it. So how would I hydrolyze an amide? Yeah, H plus or OH minus. And then it's an amide, so what do I have to apply? Yeah, you have to heat this aggressively, so like for several hours, all right? So that's how we go back. So we're kind of combining everything. I taught you about a little bit first why it's important, then I explain how it exactly works now in these latest chapters. All right, so those are the reactions I wanted to go over here, but let me just number them again. So we start from 6. This would be this one right here, 7, 8, 9, and then 10. All right. Now, unfortunately, we didn't have enough time to go over how we get OH on the benzene. But it was part of those notes I showed you very rushedly at the end on last Thursday. So if you treat aniline with HCl and sodium nitrite, you generate the N2 group. Now, that N2 group, even though it's so reactive, it's like stable. You can put it in a freezer. We did that in my group for like molecular electronics. We're trying to make basically your cell phone has organic LEDs. We were trying to make molecules that represent that or that are made up of that. So we were trying to make molecules that serve as organic semiconductors. So organic chemistry also applies to like technology too. Okay, so a lot of things here. So, but we did talk about some reactions with OH, and that's kind of the last thing I want to talk about for benzene. So maybe I could put this somewhere on the same page, so you don't have to create a new page here. Okay. So, Yeah, so for benzene, if you're wondering how this is made, I could show you, okay? Now, I'm going to put this in blue because I'm not going to test you on this, but this is how the OH is made, all right? So I'm just telling you, how would we get from benzene to phenol, which is important. So you would do, well, here, how would we do this? So let me backtrack. Let's not worry about that. Let's just talk about phenol. So it's off to the side here. Off to the side, because we also saw phenol reactions. Okay. So we could use phenol. Phenol is a good starting molecule. But phenol, remember phenol is too reactive. So phenol is too reactive. How do we, sorry, I didn't mean to write phenol twice. How do we make it less reactive? By adding a CH3 group here. So there's two ways to protect this and deprotect it. So we want to deprotonate OH, so sodium hydroxide first. And how do I get a methyl group on there? All right. Just choose any methyl X group. So the most common one to use, the easiest one to use by far, methyl iodide. So methyl iodide will allow us to alkylate it at one position. All right, now to go backwards, do you remember how we removed the OCH3 group? What we would do? I think it was an acid. So to get this group off, you would actually do HI. So you just need a strong acid. HI is probably the reagent of choice. So for this one, I would just try to remember that, HI is pretty much the one that's commonly used to remove it. That's because it's a really strong acid, and then you'll get back methyl iodide out, so you can actually maybe recover it that you used to make it up. Okay, and I think that's all of it. All the benzene we covered. Well, we didn't cover this acid one right here, but now we covered it in this current chapter, so now we kind of completed the picture. The only missing puzzle is how do we get from benzene, how do we go from, is there a way to go from one of these intermediates here directly to phenol? And the answer is yes, but we didn't have time to cover that, and I covered it really quickly last Thursday, so you're not responsible for that, okay? But all these, we have either gone over examples in class or seen them in like syntheses that we targeted as part of practice. Okay, so that is benzene. I don't think I missed any, and like on the second exam, we had some synthesis problems where we had to use these reagents like back and forth. Yes.
Are we supposed to remember like all the electrons drawing from main groups and then like if they're
So as far as synthesis, yes, you would kind of have to generally remember that order, like, which ones are the greatest electron withdrawing groups, which ones are the greatest donating groups, and all that. So we could maybe summarize that just a little briefly here. But also, if you want to remember, like say I gave you a benzene, but I gave you a donating group and a deactivating group or withdrawing group, you'll have to pick like which one should direct where the new group goes. So it might be beneficial to put that chart maybe, or just that order on your note card, just in case that makes you up. Okay, but we could close out that today's class by re-going over that again. All right, so let's go over our list. of activating and deactivating groups. All right. So H is in the center. So that's our baseline. So H is in the center, right? So to the right is going to be increasing deactivators. And to the left, increasing activation, so activating groups, activators. All right, what's the strongest deactivator? I remember. No.
Oh, the nitro group.
Yeah. So it's usually in this order. CX3. NH. NR, so not NH. NR3 plus. And then nitro. And then CN is somewhere in the mix. I think CN is somewhere over here too. So CN. Those are our strongest deactivators. So that's our strongest area. So let's group them up. Area. Then the next strongest are, oh wait, CN is actually over here. That's right. CN and then carbonyl. Or whatever that may be. That's your next strongest one. And then the weak deactivators are what? Yeah, the halogens. So that's Cl, F, Br, iodine. Well, I guess F is F. Yeah, F will kind of classify there. All right, here's our baseline. That's H. That's our baseline. All right, we'll end up here. So just a few more. So what are the weak? So this is weak, moderate, strong. So most electronegative groups charged or 2 oxygens with resonance, very lot of resonance withdrawal. That's going to be a strong deactivator. Now, how about our activating groups? What are the weakest activating groups? Yeah, anything alkyl groups, right? Alkyl, benzene. So anything with our group right there. So that's our weak ones. Okay, what are moderate? Yeah, nitrogen lone pair, but what's also attached to it? Not hydrogens. So moderate means you still can donate, but you have counter resonance in another direction. So maybe when we have a nitrogen directly attached, but the nitrogen is also attached to what? Yeah, double bond group. It has to be electron withdrawing group. So this is usually our esters and our amides directly attached through the nitrogen, right? Like that. That's our moderate ones. Lone pair is also participating outside of the ring. And then our strongest ones, where there's only, sorry, we're going over a little time, guys. Strongest one is the ones that you have lone pairs directly adjacent to the ring. So anything that's really basic, nitrogen, NH2, OH, and the one I put on exam, O minus. That's really donating, okay? And then the only exception, I guess, these are the most common ones. For whatever reason, this is an exception. Remember, we protected the OH and made it OR. So I think if there's like an alkyl group, the alkyl group will donate more electrons to the oxygen, but due to electron repulsion, it will kind of destabilize it, so it only donates moderately. That's my Yeah, so this is actually a moderate one. Moderate. All right, guys. On Thursday, please come to class. Any like follow-up questions you want? Do you want to work on maybe some more synthesis? I'll be open to that. But and also review aldehydes and ketone reactions because that was a big part, including aldol. Okay, that'll be it for today. Thank you.
Off my notes,
Yes.
all the
Yes.
chapters
Yes.
are.
All right.